You really want to walk away from this experience here reaching total mastery of the Common Core. Because in your careers in scientific computing, at least for the next 10, if not the next 20 years, OpenMP will still be going strong. For reasons we can talk about later, eventually it will go away. But it will go away because the base languages will incorporate all that functionality. If you look at where C++ is going, C++ will eliminate the need for OpenMP, SYCL, and CUDA. And it'll take it a decade to get there. But if we're lucky, in a decade, you'll just learn C++. And then what happens is the C and Fortran language communities watch C++ and follow in that suit. So, and there's some very specific examples of that. So, you know, when it comes time for you to teach your children parallel programming, you probably won't be teaching them OpenMP. And you'll be able to sound like me, you know. Yeah, back in my day, they put Pragma OMP parallel. Yeah, okay. So let me talk about my solution to this problem. And is that I guess it is. Good. It's not very readable on the monitor they show me, but okay. So here's my solution. And I'm trying to remember everything I did. The big thing that you have to get done first is to recognize that we're running into that rule on the variable C. If it's a file scope and now you're going to privatize it, things get messy. So what you do is you create a private copy of it and then pass it in as an argument to test point. So now I've disambiguated to the compiler exactly what that test point is. I'm sorry, what that C is. So that's one thing I had to do. Another thing I had to do was in the algorithm for the Mandelbrot set, you need to put a little shift. You need to perturb the points you select. So you're not just selecting these whole numbers. So that's what that EPS does. But notice in the original one, I privatized it, and it needed to be first private. So I needed to make it first private. Now, could I have just not made it first private and just let it be shared? And their answer is yeah. And this comes down to another thing about old guy thinking versus new guy thinking. You know, old guy thinking, it's like, hell no, there's no way that compiler is going to know that it can promote that to a register and not have to read that out of cache every time. So no, I've got to make it first private. I can't imagine any compiler today that wouldn't look at EPS being shared and wouldn't know to promote that to a register for you without you doing anything. But this is, you know, the fact I had to put first private EPS is another sign of my old guy thinking. That, you know, I just don't want to get in the habit of trusting compilers. Because compiler writers are brilliant and very smart. Compilers are stupid. And I'm trying to break myself of that habit, but it's hard. Yeah, I have huge respect for compiler writers. Early in my career, I did a lot of work with Ada. And I had to write, how many of you have even heard of Ada? I mean, that's, okay. That's not an old language, at any rate. And I had to build an automatic test suite. So I had to build an Ada parser. And oh my God, I think of all the software I've written in my career, nothing was more difficult than writing that Ada parser. And that's just step one of what a compiler writer has to do. So I have profound respect for anyone who can write a compiler. It's not me. So at any rate, I changed test point. So it takes an argument for the complex variable. I had to make EPS first private. The other thing is num outside is a global. You had to protect that update with the synchronization. Yes?
If you make num outside, like you return it, does this change?
So what he's talking about is an interesting innovation, okay? Num outside, I'm leaving it global and doing a critical, which is probably not too horrible, because if if multiple threads aren't hitting the critical at the same time, the overhead of a critical is not that bad. So if you time it, you might be okay with that critical. But as part of the extreme scalability mindset, it still is a mutual exclusion operation. It's still pretty ugly. So if you're going to think extreme scalability, and I have to keep reminding myself, that's what we're supposed to be all about, right? We're here for, because we're extreme. We're not mundane scalability. No, we're extreme scalability. Okay. Extreme scalability, that critical inside a loop like that should make you just freak out a little bit. So what do? Many things. My favorite solution is you return num outside. So now that void test point, I make it an int, and it now returns num outside. And now inside this loop, I have a reduction over num side. That's a much more scalable solution. I had to make more changes. See, that's what I like about this exercise, is it has multiple layers, and there's even more. So this is a good one to sit around and play around with and see what can you do to make it run even faster. All right? Let's move on, because we've got, oh my God, a lot of ground to cover. So memory models. All right. We are now going to talk about memory models. Okay, no one's running out of the room. Oh, that's good. Yeah. You thinking of running out of the room?
The first one, I mean, in the manual.
Oh, you want me to go back? See, oh, good strategy. He's trying to keep me from talking about memory models by diverting me back to this one. Yeah, okay, smart move. Why did we make J private? That's very important, because this is a nested loop. And if I don't make J private, I now have a race condition on the loop index, because J would be shared by default. See? Pragma OMP4, this is really important. The for construct makes the parallel loop control index private. If I have nested loops, then it doesn't make it private by default. So that J, if I don't do something, is a shared variable. Why you would ever want a race condition on a race on a loop control index, there's nothing I can think of that would make that correct. So I have to tell it to make it private. So this is very important with nested loops in OpenMP. That, you get so used to putting that pragma OMP parallel for, and you don't have to privatize the loop control index. Well, you do if you have a nested loop. Is that clear? Okay, good. Any other attempts to delay me from talking about memory models?
Yes.
Yes.
Do int I and int j in the for loops. That's not ever a problem, right?
That is correct. In fact, I often do that. So the question was, could I just privatize I right there? And yes. So, and I often do that. I would rather have too much information than not enough. So I would probably put private C, comma, I, comma, J. It doesn't hurt anything to explicitly privatize it. All right. I'm now going to say a little bit about memory models. I promise, just a little bit. Okay? Memory models. Oh, my God. Let me tell you a little story about memory models. Long, long ago, in the long ago time, a group of very, very bright people at the magical land of UIUC, University of Illinois, Urbana-Champaign. Gosh, it's supposed to be Champaign-Urbana. Anyway, whatever. UIUC. Got together and said Java needed a memory model. Now, a memory model defines what values can be loaded when you load a variable. Sounds easy, right? I do load on gamma. Well, give me the value of gamma. Oh, yeah? Really? OK, let's think about gamma. All right, look at this picture right here. A dual core chip. We're not even going to go to lots and lots of cores. We're not NUMA. We're not going to have, it's just simple 2 cores. OK? Well, each core has a register file. Each core has a level 1 cache. OK? Actually, there's probably a shared level 2 cache. I'm sorry, there's a level 2 cache that has the instruction cache and the data cache, and there's the level 3 cache. And let's just keep it simple, though. We have the level 1 cache and a shared last level cache. Oh, and then we have the DRAM. What I want you to realize is there is a value for the variable gamma in each one of those locations. And so when I say I do a load on gamma, what value do I read? That is not an obvious question. And a memory model defines unambiguously the rules that state what value of gamma would you see on a load. All right? So, our friends in our story at UIUC go on to create a memory model for Java. And they proceed to burn years of their life, and they do this. And they publish it to great fanfare, and there's great celebration. We now have a memory model for Java, and they released it as part of the language, and off they went, and people were very excited and found out it broke all over the place. There were cases it just didn't work at all. So our intrepid crew got together again and burned more years of their life. You know, burned graduate students. That's what we do, right? You know, they're the expendable currency. I'm sorry. I bet some of you are graduate students, right? Yeah. At any rate, they updated the memory model. And these are very smart people. So, yep, it's great fanfare. We've got a working Java memory model. And it broke. It got out there, and people came up with all sorts of cases where things that by the memory model were race-free. You know, you would get a consistent result no matter how the ordering of the threads ran. And you could find cases where it fell apart. Along comes the people in the world of the language known as C++. 3 simple characters for one language, a language that I have come to not retch when I look at. And they said, you know, we're going to build threads into the core of language. This will be the version of the language we will release in 2011. And we're going to put threads in the language. The second you put threads as a first-class language item, you must have a memory model, because now I have multiple threads doing a load. Well, fortunately, we have these really smart people who failed twice with Java, and we know the old saying, third time's the charm. Okay, well, this will be their third time. It's got to work. So they got together, burned lots of graduate students, spent years of their life, or what probably felt like decades of their life. But they came out with a really elegant, amazing piece of work of a C++ memory model. And those of us, as I said earlier, those of us in the languages community, we follow what those C++ people do because it's a cool, cutting-edge language, and it gets the most aggressive academics pushing the envelope today tend to do it around C++. So it's kind of natural to follow in their footsteps. So I was writing the memory model for OpenCL, a GPU programming language, which all of you have used, right? No? Oh, anyway. And so I did the rational thing. It's like, I'll base it on the C++ memory model. Okay, we're really excited. We're like, 3 months away from releasing OpenCL. And I get a call from my good buddy on the C++ standards committee saying, stop, no, we found a bug. We found a bug in the C++ memory model. It's called the out of thin air problem. And I won't bore you. In the long, drawn-out version of this anecdote, I would explain the out of thin air problem. But it's like you can have multiple threads all writing 4, and it's going to return the number 42. It's like some magical value appears out of thin air. That's why it's called the out of thin air problem. And so, fortunately, they told us before we released our spec, but it was too late to make changes, so we had to put a footnote in there, saying that, yes, we've got this great memory model, but given these conditions, you could get an out of thin air problem. All right. Now, the reason I do all this, and I go on and on like this, is I want you to understand how scary it is to deal with memory models. They are painfully, painfully difficult to get right. And just to put it well grounded, when you look at a picture like this and I ask you, for any given situation in your code, what value of gamma will be returned, this is not an easy question. And it does not have an easy answer. So be cautious when dealing with code that depends on subtleties of the memory model. Be very cautious. So, there are many, many flavors depending on the conditions you put on the shared memory in your program. There are a collection of memory models that put different constraints on what they deliver. It turns out that as far as I know, any practical system with multi-threading permits something that's called a relaxed consistency memory model. What relaxed consistency means is that when I go back to this picture here, a valid program is allowed to have different values for gamma across this picture. Now, I could write a memory model that says gamma must always have the same value everywhere. It would be a sequentially consistent model. Okay? I know that for every interleaving of my code, there will be one correct order of values to gamma, and everyone will see that order. Sequentially consistent. And we know how to build systems that way, and they would run so slow you would never ever want to use them again. Okay? So what virtually everyone does is relaxed consistency, which basically says you are allowed for each thread to have a temporary view of the values of the variables, And those temporary views can be different. All right? So what you have to do is you have to define an operation that says, okay, make it consistent. So there's an operation in OpenMP, and you know, every multi-threading environment has a flavor of this. There's an operation in OpenMP, it's called a flush. And it basically says, make my temporary view consistent with the value in DRAM, consistent with the value in memory. That's what flush does. Flush on its own is not a synchronization construct. Remember, synchronization always defines an order constraint between two or more threads. So flush doesn't provide an order constraint. The raw flush by itself doesn't provide an order constraint. It just says that, well, my view, I'm a thread, I called flush, my view is consistent with the value in memory. Okay, cool, I don't care what the rest of you threads do, that's your problem. But at least my view is consistent. So that's what flush does. And this is the key to a relaxed memory consistency model. Okay, are people scared yet? That's kind of the goal. This stuff's scary. So that's the flush operation. So what it says is if I put a flush in my program, and it's just the bare old-fashioned flush. There are variations on flush that have been added more recently. But if you put a flush in a program, it says if I look at all the variables that this thread is working with, any reads or write by that thread are complete and visible to other threads before I leave that flush. I'll have an example in the next slide. And no subsequent reads and writes have occurred in that thread. Now, the reason this is so important is compilers aggressively reorder operations. You don't even think about it. But when you write a piece of code, the compiler will get very smart, and it'll figure out that, well, you said do this statement, then this statement, then this statement, then this statement, but I know if I do this statement up here and this statement here, you're going to run faster. So it aggressively does all this reordering. And the problem is that compiler doesn't know about multiple threads, it just knows one thread. What if those reorderings will break a program and viewed from another thread? So flush basically says, compiler, don't move statements around this. I'm controlling what you're allowed to reorder, and you can't reorder around the loads and stores touched by this flush. Phew, that's a lot, man. It's a lot. Just keep it all straight in your head. It's easy, right? So this is the way it would look in a piece of code. Imagine I compute a variable A, and I want to make sure that the other threads will see it after my computation. All right? Well, too bad, because flush isn't a synchronization construct. I have to do a bunch of other stuff so that other threads will see that order. But at least what I can do is I can say, yeah, I've completed it. Yeah, write it to memory. So that's what this flush does. Now, normally at this point, I would stop and I would say, any questions? But I'm going to tell you right now, no questions. Really, because my whole point is, don't use flush. Do not write code that needs flush. Know it's there. Be aware of the concept. All right? The concept is important. But basically what we do in OpenMP is because our target audience are application writers. They're the physicists, the chemists, mostly the chemists, because we must admit, chemistry is like the coolest of all subjects, right? Right? Yeah. Okay. My PhD is in chemistry. But I did physics for it. Oh, well, it doesn't matter. Because we are basically targeting OpenMP first and foremost to people who are principally not computer scientists. You know, if you're a computer scientist, you take courses on concurrency theory, and you know more about memory models than I do. You study it, and it takes that study. But OpenMP is for application programmers from outside computer science. So what we do is we imply a flush. If you use our high-level synchronization constructs, you don't have to put the flush in. We put it in for you. And so think about it. When I enter a parallel region, I do a flush. OpenMP does a flush. At a barrier, whether it's an explicit or an implicit barrier, OpenMP puts a flush. And then on a critical section, on entry and exit from a critical region, from a critical section, OpenMP implies a flush. So there are flushes there. I want you to know they're there. But you don't have to think about it until you start getting wonky with writing complicated synchronization protocols. So for example, if I want point-to-point synchronization, thread number 7 needs to finish this and let thread number 11 know before thread number 12 moves forward. Okay? When you start doing stuff like that, that's when you have to deal with flush. Okay? Now, my advice. When you find yourself wanting to write code that needs those kinds of wonky synchronization patterns, don't write it. Seriously, don't write it. There are people who that's what they do for a living. Find one of them, pay them what they need. Usually cases of beer are good, but yeah, that's how I got my beer in grad school. All the biochemists I hung out with didn't ever want to write code, and so yeah, just a case of nice beer. At any rate, get a professional to write it. And even myself, I'm a bona fide expert on this topic. I wrote the memory model in OpenCL. I'm an expert. If I needed to write a lock-free data structure, that's kind of data structure where I don't, it's like for the queue I mentioned for managing dynamic. I would do that as a lock-free data structure, and you don't even want me to go into that. I would go to an expert to write that. I wouldn't try to write one myself. I know how. I could teach you how. It would probably work, but would I bet my life on it working? No, they're professionals only. So you need to be aware of that, okay? Phew, that's done. Let's move on to something more fun. Okay? Say it wasn't too bad. Memory models. Now you all know memory models. Isn't that great? You don't need to take a course in it now. If anyone tries to tell you you need to take a course in concurrency theory. So let's talk about irregular parallelism. So what we've covered so far in OpenMP is pretty much old-style OpenMP. Let's say prior to 2005-ish. And for most people, that's what they use. The problem is there's a lot of algorithms that just don't fit into the straight SPMD pattern, and that just don't really fit into the loop-level parallelism pattern. Find your loop, put a pragma parallel, pragma OMP parallel 4. Got to get the words in the right order. Okay, look at this code right here. So I'm going to walk a list, and I have a while loop, and I'm going to walk the list until I hit the end of the list, which will trigger the condition on the exit of the while loop. And I'm basically, for each node in this list, I'm going to do some processing. Now you may go, well, you don't write code like that in scientific computing. Yeah, you do. There's several n-body codes, for example, where you create lists of spatial trees that you walk to update the contents of that list, because you have to know what galaxies are in which list. I mean, these things come up. So in original OpenMP, they were not easy to handle. Do we want to do this exercise? Yeah, I've been talking for 30 minutes. All right. Here's what I want you to do. In the repository, there should be a file, a program called linked.c. We're going to spend 10 minutes. For most of you, that'll just be time to start thinking about it. All right? We're going to spend 10 minutes, try to parallelize that. And let me give you a big hint. Just worry about the while loop and main. Don't look at the functions. I mean, we created some busy work for each routine to do as it processes each point in the list. Don't look at that at all. Just think about the while loop in main. We're going to spend 10 minutes. How would you parallelize that? And maybe one or two of you will be able to do that in 10 minutes. But I want you all to think hard about using what we have discussed in OpenMP so far. That's everything you see on this list. How would you parallelize that thing? Parallelize, not paralyze. They're different. Okay. In the multi-day version of this, we take long enough for you to really flesh this out. There's a lot of learning opportunity in exploring the different ways to parallelize that code. It's ugly. Okay, that's just all there is to it. So here's how I did it. And there's multiple ways. You know, I enjoy it when I do get to do the multi-day version of this course because then I see the different clever ways people attack this problem. Okay, here's how I attacked it. I walked through the list once to see how long it is because I don't know how many items are in the list. So I first want to know how long it is. All right? Then I have to malloc an array to hold all those pointers. Okay? Because I'm a C programmer. I don't know this weird new thing. Then I walk through the list and I save each of those pointers in the list. And I save them. So now I've got an array. So I've basically created an array that holds all the pointers to that list. And so now I can do a pragma OMP parallel 4 and do that in parallel. Can we agree that that's really ugly? I mean, what a horrible, awful thing to do. And, you know, I played around with the schedules, and I found that if I used the default schedule, I went from 48 to 39 seconds with 2 threads. If I used static 1, it went from 45 seconds to 28. Now, I want to pause for a moment and explain why that works so well. So remember, if I use a dynamic schedule, there's all this overhead of going back and checking, you know, is the queue ready for me to spit out a new one? By design, the work that we do for each node in this list is highly variable. So if I just split the loop by giving one block to one thread, one block to the other, that's what happens with default, there's a load imbalance problem. So load imbalance means that you're not keeping all of the threads equally busy. Remember, it's when the slowest thread is done, it's when you're done. So your goal, and this is true in MPI, this is true everywhere in parallel computing, your goal is that everyone finishes their work at the same time. That's what the load balancing problem is. So a common trick when I have a whole bunch of work per loop iteration is static with a very small chunk size, in this case 1. So now what I'm doing is I'm statistically distributing, in this case dealing them out like a deck of cards round robin. So I'm spreading out the loop iterations. And so I'm just saying, you know, if I spread it out enough, chances are I'll get a decent load balance. Nothing to prove it. It's not as fancy as a dynamic, but it's amazing how often that works. And the overhead in managing a static distribution is much lower than dynamic. So at any rate, that's where we go with there. The bottom line is that sucks. That you don't want to write code like this. You know, to make 3 passes through my list, to walk that data, to 2 passes to get the array, and then I go through the pointers again in the array. That just sucks. There's got to be a better way. And there is. So I believe this went into OpenMP 3.0, which was mid-2000s, 2005-ish, I think, maybe a little later. 3.5 is when we really got it nailed down. So, that's when this came into existence. And we defined the idea of a task. A task is an independent unit of work and the data environment associated with that work. So what we're doing here is we are decoupling the concept of a unit of work from the concept of the unit of execution that does that work. And this is why it took us order 6 years of work to get this into the OpenMP standard. We had working proof of concept implementations around 2000. It was 2005, 2006-ish before we actually had it in there. Because we had to go back and rethink OpenMP from the beginning to support this idea that you have the decomposition of work, which is a task, from the thing that does the work, which is a thread. And if you read the spec right now, you'll see some really convoluted language. The initial thread will encounter the task construct and then create the thread, which will be the initial thread of the new execution context. It gets really bizarre. It's one of my complaints about OpenMP. The spec is all but unreadable to a normal human. That's why you need to buy books by people who write about OpenMP. So, here's how it looks. You got a structured block of code with the task. Imagine I have a serial program that does the pink and the blue and the greenish and the bluish. And what we do is when a task encounters a task construct, it'll package up the code, it'll capture the data environment and package that up and plop them on a queue. And then as an execution unit, a thread finishes the task it's working on, it'll go and grab another task. So the execution will look like the right side of that screen. And so I get nice parallelism. But because I've decoupled the unit of work from the thread, and I've decoupled the expression of units of work that can execute concurrently, I've decoupled that from the flow control of the program, I'm now not tied to a for loop. I'm not tied to a while loop. I'm not tied to any particular control structure. So this brings about huge amounts of flexibility in OpenMP and allows us to do all sorts of cool stuff. So this is what the task, there's a real common pattern in working with tasks. And the idea is you want to designate one thread running its task. I'm sorry, I'll not drop into formal task jargon because it gets really convoluted. I'll have one thread out of the team, and I'll say, hey, you, create all the tasks, the top-level tasks. And everyone else will wait and execute those tasks as they become available. This is what the single construct does. It's classified as a work-sharing construct, like a loop, the for construct or do construct. They're work sharing because they take a block of work, in the case of for, it's work associated with a loop, and splits it up between the threads. Well, single is the same thing, it's just giving it to one thread. And all work sharing constructs have kind of the similar behavior pattern. They define the work that's going to be shared among a team of threads, and then everyone waits at a barrier at the end of the construct before anyone continues. So looking at this construct, I create a thread. I do in parallel a whole bunch of stuff. Then I have the single construct. And imagine I wanted one construct, one thread, to exchange some boundary conditions, to do something where it's so convoluted and mixed, I would just want one thread to do it. That's where I would use the single. And all the other threads are waiting at the end of that bracket at the implied barrier. And then when they're all done, then I can go and do the next step. So that's the single construct. So one thread's going to do the code in the construct. The other threads are waiting in the barrier at the end. Do you think we have a no wait? Pragma OMP single no wait? Of course. Yeah, it's a work share construct. If I'm going to put an implied barrier, I have to have a way to tell the system, don't put that implied barrier there. We're extreme scalability. You have to be able to turn off barriers when you know it's safe. So you can have Pragma OMP single with a no wait to turn off that barrier. Okay? So now here's the task directive. And this is a common pattern for how it would be used. So I create a team of threads, pragma OMP parallel. And then I say, OK, one thread's going to create the top-level tasks. The other threads are going to wait at that barrier to do the work. So, oops, I forgot, have these builds in there. Right. OK. So create a team of threads. One thread packages up the tasks. That's the single. And then I have the tasks, pragma OMP task. And that can be blocks of code between curly brackets. But if it's only one line, I don't need the curly brackets. So I have a structured block for each task. So one task is Fred, one task is Daisy, one task is Billy. They're not ordered. They're going to be dumped in a queue. And all those threads sitting there waiting at the barrier will start working on Fred, Daisy, or Billy when they get a chance. Now, there are so many subtleties. I'm going to mention just one of them right now. An implementation has the freedom to look at one of those functions. So imagine the thread that's the single looks at the function Billy and says, you know, this function isn't doing enough. It's really trivial. It can just execute it. So it has the freedom to say, we're just going to go ahead and execute each of these. So we call it deferred execution. It's potentially deferred. But logically, put it on a queue. The other threads will execute it. Block practice drill. OK? Very simple. I want to see if you really understood how to use task and how to use a single. So in the jargon of computing, we have something we call a race condition, not the same as a data race. A race condition is a program that gives you a different answer potentially depending on how the low-level threads or processes are scheduled. It's not always it's an invalid program if it's due to a data race, but you can have valid programs that have a race condition. All right, using tasks, write a program with a race condition where sometimes it'll say, I think race cars are fun, or sometimes it'll say, I think car races are fun. Ruud van der Pas brought us this exercise. I'd like to acknowledge sources. So you're going to write a program using tasks with a race condition. And basically the idea is the task will print race or car. And depending on how those tasks are scheduled, I will get, I think race cars are fun, or I get car races are fun. Does that make sense? OK, go for it. And do I have serial code for this? I do. OK, so there's something called RACE, right? Yeah, so there's serial code for you to start from. So as I said, the purpose of this exercise was to make sure you really understood how to use single and how to use the task construct. There's not a lot of subtlety or fanciness in this one. But you need to create the threads, pragma OMP parallel, and then you say one thread go through, pragma OMP single, and create my tasks, car and race. So I print, I think, before the parallel region. I then have my tasks for doing car and then doing race, and then I have print apostrophe S and R fun. And this might, depending on how your runtime system handles this, I have a feeling that some runtime systems look at those simple print statements and just go, I'm just going to run it. All right? So I've often thought, what if I put them in functions and then link the functions in separately? And another thing I've played with, I have a program I call Schrodinger's program, where I went through and I did all sorts of weird stuff with random number generators to give them tasks posted in different orders. And so, at any rate, as I said, the big thing was not to create a race condition. It was to, do you understand single and tasks? And you now all understand singles and tasks, right? So just pause for a moment and think how wonderful this is. You know how to create threads with a parallel region. You now understand how to design algorithms in MPI because of the SPMD pattern. Okay? So you know MPI now. We just have to, how do you spell things? You know about parallel loops, and now you know about tasks. Just an amazing breadth of knowledge. And it's all just so fun and elegant and cool. So the data scoping really kind of works about what you already know. You know, if I have a shared variable, when I hit a task, it's going to point to that location in memory as that location was attached to the variable when it encountered the task. Everything is when it encountered the task. When I have a private variable, it will create an uninitialized variable that's private to each task. If I have a first private, it will say, I will create the private variable, and I will copy into it the value of the original variable at the time the task was created. Now, when we were sitting down and discussing this, creating this, someone wanted to create a new clause called capture. Because that's kind of what you're doing. You're capturing the copy. But I pushed back hard and said, let's not pollute the API, because that's exactly what first private does. So let's just call it what it is, first private. So that's the basic data rules. So if you think about this case here, I have, pragma OMP parallel, shared on an A, private on a B, and now I create a task. All right? So A is shared because it was shared by default. C was declared inside the task. It's, of course, private. Why is B first private? And here's why. If we, once again, the principle of make the default behavior the likely behavior programmers would want and prefer. If you have a variable that is private when you encounter the task construct, so you earlier specified that I want each thread to have its own copy of this variable, so it's private. We believe most times you do that, you have a value attached to that variable that you want to associate with the task. So the default behavior on private variables when you encounter the task is to copy them into the task as first private. So this might look a little weird. It's a little different than maybe you would think with nested parallel regions. But this is what it does. We make it first private by default. OK? Questions? All right. You now know tasks. And you know tasks so well that you can go back to that linked exercise, not the one where you did it with convoluted doing it without tasks. Go back to that original linked exercise and traverse that linked list in parallel using tasks. And we're going to this will take 10 to 15 minutes, I predict. All right? And remember, just focus on that while loop. Don't get all into the weeds of the computations inside the processing each node in that list. Just think about that while loop and parallelizing that.